everybody. In the last class, we discussed, actually we finished with the statement of Cayley-Hamilton theorem. Here, the statement of this Cayley-Hamilton theorem says that suppose if this capital A be a square matrix and this is the characteristic polynomial of that square matrix, then characteristic polynomial means this kind of expression where in place of x we have lambda. So we can say that this expression is actually is equal to determinant of 1 minus lambda into I, like this. So this is the characteristic polynomial. Then the statement says that if in place of lambda we put this determinant capital A and compute this expression, in place of lambda we are putting this kind of determinant capital A, as because it is a square matrix, so a square, a cube and all up to a to the power of n, all these matrices must exist. And the statement says that this expression will be equal to the zero matrix. It will be a matrix because over here, yes, we can see that this is actually a metric polynomial. So over here, this expression is equal to 0. We need to prove this result. We need to prove that this, if over here, if we put in place of lambda, if we put lambda is equal to a, in that case, this total expression becomes is equal to a zero polynomial, a zero matrix. Okay. So this will be the expression of the characteristic polynomial. Just I am writing this expression in terms of small x, just in order to repeatedly in order to avoid this lambda, because typing lambda in the keyboard is a bit difficult task. So in place of lambda I am writing x. Okay. So over here this is a polynomial of degree n, and it can be shown that the adjoint of this matrix A minus x into I, adjoint of this matrix is also a metric polynomial, and its degree would be n minus 1. It can be shown that adjoint of this matrix A minus x into I is also a metric polynomial of degree n minus 1. As because it's a metric polynomial of degree n minus 1, therefore this expression can be written in terms of a metric polynomial like this. We suppose that b0 plus b1x plus b2x square up to, you see, the degree is n minus 1. So we are taking the term up to x to the power of n minus 1. Its coefficient we suppose that be n minus 1. Alright. So this is the adjoint of the matrix A minus x into I. Now we have a relation that if the matrix A is multiplied by its adjoint, then this is equal to determinant of that matrix A minus x into I. That is actually, this is the determinant symbol, not the modulus. Okay. Determinant of this kind of quantity A minus x into I multiplied by the identity matrix I. If A is a matrix of order n, then this identity matrix should also be a matrix of order n. Okay. Now let's see what does this relation give. Let me show you the computational part now. Let me first write the expression of this adjoint of A minus x. I am keeping this expression in same. And what is adjoint of A minus x? This is the adjoint of A minus x. It's the metric polynomial of the n minus 1. That is equal to What is this? This is the determinant a minus x into lambda. Mind it, a determinant is always a real number. Determinant of matrix is always a real number. That's why we have written in terms of this real number x. So do not mix them, because it is sometimes becomes very difficult to distinguish them. Anyway, so multiplied by the identity matrix I. So over here, this scalar quantity, this is a determinant, or scalar quantity. This scalar quantity is multiplied by this identity matrix. So on the right hand side, we have a n cross n matrix. Again, if we multiply them on the left hand side, we shall also have a matrix of order n cross n. Now let's try to find out the let's try to first expand them and try to find out the similar terms in x. In fact, this is an identity. This result is true for any real number x. So we can say that this relation, whatever we shall have in the subsequent computation, that would become an identity in x, okay, in this real number x. So let's see what we have. Over here, this is the matrix. So capital A is to be multiplied from left by this kind of expression minus x into this identity matrix I, that is to be multiplied by this kind of determinant from left. This is a left multiplication. That is equal to, let me write it in the next line. Just a minute, please. Okay. Let me write this expression on the right hand side. So this is the expression, and you see over here this I is to be multiplied by this real number. So whenever this I is multiplied by the real number, we actually have this kind of expression, a0 into I plus a1 into I into x. You can write it, write I anywhere in this expression. I am writing it over here, just in order to make that this is an expression or the coefficient of x to the power of n. So we shall have this type of expression like this. Now let's compute the left hand side part. Over here, a, this determinant a is to be multiplied by the total expression from the left hand side, not determinant, that is actually a matrix. So this matrix A is to be multiplied from left on each and every term. So let's see what we have. This is capital A from left multiplication. It is to be multiplied by left. You see, matrix multiplication is not commutative. You cannot interchange their position. Again, over here, this I is to be multiplied by from left, but I into b0 is actually is equal to b0. It doesn't matter whether we multiply from left or right by this I. Along with that, we have an x. So I is not a factor over here. You can multiply from left, you can multiply from right. So I is not a factor, but over here x is a factor, and x is a scalar quantity. So over here you can write b0 into x. Then with this negative sign, we have b1 into x square. Again, this positive sign will be negative because I have removed this bracket over here. So that would be x cube, and afterwards minus dot 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 minus n x to the power of n. So I am actually basically I am just multiplying this expression by x, because multiplication by identity matrix I will remain this expression as same as it is. Now let's copy and paste it. Now let's try to combine the similar expressions. Over here you see this expression can be combined with this one because x is there. So let's this x is a scalar quantity. So we can take this x common. So this would be the coefficient of x. Similarly, x square. This is the terms. These are the terms containing x square. So let's take this x square common, and so on. I'm not writing this b2. Let me write one more term for you. That the next immediate term would be a into b3, a into b3 into x cube. So this term will be adjusted with this term, and we can take this x cube common. So we have this kind of term and so on, and finally these two term can be this is a into b to the power of n minus 1, and if we continue this fashion, then ultimately the x to the power of n, its coefficient would be what would be the coefficient? You see, you can observe a pattern over here, a into b3 minus b2. So over here, a into b2 minus b1. So what would be the coefficient of x to the power of n minus 1? The coefficient of x to the power of n minus 1 will follow this same pattern, a into b n minus 2, sorry, minus 1 minus b n minus 2. But the last term would not follow any pattern. It is an independent part. So the last term remains this one. This b n minus 1 into x to the power of n. That would be the last term. Now you see, this is an identity in x. So comparing the similar terms, we get what we get. Let's compare the similar terms. We get these relations. Say the first one would be a into b0. This constant term will be is equal to this constant term. Is equal to this kind of expression. And afterwards, this expression, the coefficient of x, this coefficient of x would be is equal to a1 into I. Then this coefficient of x square, this expression would be is equal to this a2 into I, and so on. And finally, what we have, this is the term n minus first term, that would be is equal to what would be its immediately n minus first term. Over here, the n minus first term would be is equal to a n minus 1 into x into I into x to the power of n minus 1. So that would be the term with x to the power of n minus 1. So therefore this right hand side, let me copy this right hand side, and this that would be a n minus 1. And the last term, this is an exceptional case. The last term is minus en is equal to this an into I. Okay, so this much relations we have. And now if we multiply the first relation from left side, that means p multiplication by left, or p multiplication, or you can if you cannot remember this word, you can simply write multiplying the above relations from left, the above relations from left by by what? Let us first multiply the first relation by the identity matrix I, then the second relation by A, the third relation by A square, and so on, and dot dot dot, and the last relation is multiplied by A to the power of n. From left hand side we respectively get what we get. Let me just copy and paste this one after this line. So let's multiply. The first is multiplied by I, so it remains as it is. It does not change at all. The second one is multiplied by A into A from left, so like this. Then the next one is multiplied by, let me write it in this fashion, A into B. Hopefully that would be a bit easier expression for you. Next one is multiplied by A square. A square from left side. Got it? And similarly, this last one is multiplied by A to the power of n minus 1. Okay, from left side. This is multiplied by A to the power of n minus 1. And the last term is multiplied by A to the power of n. A to the power of n from left side. Okay. So this is the expression. Now if we add all this expression, let's make it a bit simple. This I into A into B0, you see multiplication by an identity matrix, it does not change the expression at all, so we have this kind of expression on. Now this A into A square multiplied by B1, so this expression can be written as A square into B1 multiplied by A B0. Then this expression would be this A into A square into A, that is actually A cube. So we have this kind of expression. This is A square B. This right hand side would be simply this. You see, this is a scalar, so we can shift it on the left side, and in that case, multiplication by this identity matrix will make it capital A on. Similarly, forget about this product symbol. This is a scalar quantity. You can shift it on the left, and we shall have A square on this right hand side. And we can continue it in this fashion. This would be A to the power of n. So let's write it A to the power of n. So this is A to the power of n minus 1. Again, this is a scalar quantity, so let's write it on the left, and multiplication by identity matrix will keep it as A to the power of n minus 1. Again, this A to the power of n into B to the power of bn minus 1. And this is again a scalar, so let's keep it on the left side, and multiplication by identity matrix will keep this symbol as the right hand side as equal to A to the power of n. Alright, so these are the simplified form we have after multiplication from the left side by this kind of relations I, A square, etc. Now let's add all these results. Okay, adding, we get what we get. If we add all these results, you see this A B0 will cancel with this minus A B0. Again, you see this A square B1 will cancel with this minus A square B1, and so on. This term will be cancelled with the next immediate term. This term will be cancelled with the previous term, and you see an into b to the power of n minus 1, an into bn minus 1 will cancel with this a n bn minus 1. So on the left hand side, everything will get cancelled. So on the left hand side, we shall have the zero matrix. Remember, not any ordinary zero scalar, because these are actually matrix addition. We shall add all these matrices on the left. So we shall have zero matrix. We shall have n cross n zero matrix is equal to, let's see what we have on the right hand side. You see, we have a0 into I. Just let me copy and paste them. Then a1 into capital A plus a2 into a square plus dot dot dot. This is a n minus 1 into a to the capital A to the power of n minus 1 plus this expression. So you see, this right hand side expression can be written in this way. We can check that over here you don't need to manipulate it at all. Just keep it in this fashion. Now just I want to write this right hand side is equal to 0. I am just writing this 0 from left to right. I remove this expression, so this expression becomes is equal to 0. This much I want to change. So what we have, this is actually, you see, this is the metric polynomial. We can look at this expression. Sorry, I forgot to write one thing, that this is equal to I, just in order to adjust that this is a matrix. Otherwise, it would be a simply scalar a0. So over here, a0 into I plus a1 into capital A plus this would be a2. In case of a2, we shall have this is a2 into capital A square. Similarly, an into capital A to the power of n is equal to 0. You see, we got this relation starting from a0i to an a to the power of n. We got this relation starting from a0i to an a to the power of n. This total summation becomes is equal to 0. Got it? So in this way, we ultimately complete the proof of this Cayley-Hamilton theorem. Let's start the application of this theorem in order to find the inverse of a matrix. Computation of inverse of a matrix using this theorem, Cayley-Hamilton theorem. Let's try copying, pasting this stuff. Okay. So computation of inverse of a matrix using Cayley-Hamilton theorem. Now let's give an example over here. I think that would be a very good one in order to understand this one. So now let's consider an example. Let's consider the example that let capital A is equal to this kind of 3 by 3 matrix. So 3 by 3 matrix. Let's consider 0, 0, 1, then 3, 1, 0, then minus 2, 1, 4. Okay, capital. Now, what we need to do, we need to find capital and the inverse of capital A. Find A inverse. Okay, we shall use this Cayley-Hamilton theorem in order to find the inverse of this matrix capital A. Now we need to find at first the characteristic polynomial of this matrix. So we can write them. This is a matrix, not determinant. So let's write them in matrix notation like this. This is capital A, the matrix. We have to find out the inverse of that matrix. Okay. So how to find the solution? Given matrix is capital A is equal to this kind of matrix. Its characteristic polynomial What would be the characteristic polynomial? You see, that would come from the determinant of A minus lambda into I. So that is actually the determinant of this kind of expression, minus lambda, determinant minus lambda. That is the determinant expression. So I have the book open over here, so I am not going to expand it. We can check the total expansion. Ultimately we will have minus lambda cube plus 5 lambda square minus 6 lambda plus 5. That will be the total expansion of this determinant. So this expression is actually the characteristic polynomial. Now over here we can say by by Cayley-Hamilton theorem, Cayley-Hamilton theorem, we get, or we have, what we have, you see, in place of this lambda, in place of this lambda, we will have to put the determinant, this matrix capital A. So just put this matrix capital A over here. You will get that this is equal to 0. That is actually the 0 matrix. So you can write that is equal to 3 cross 3 matrix. 3 cross 3 matrix. Okay. And from this relation, you see, we can, in order to compute the total expression, from this relation, we have to compute the inverse of the matrix. So, just for the convenience over here, I'm just writing it in this fashion. You don't have to bother it. It is actually the character of the software, a feature of the software. So now you see, if we multiply this relation from left side by A inverse, if you multiply this relation by A inverse, what we have actually, you see over here, I am multiplying this relation by A inverse. So we can write it in this way, multiplying by A inverse from left. We get what we get. Let's multiply this relation by A inverse from left side. Okay, so we shall have minus over here A inverse, over here 5 A inverse, then 6 into A inverse A plus 5 into A inverse, and on the right side we shall have A inverse into 0. That is actually the 0 matrix. That is the 0 3 cross 3 matrix. 0 matrix. Now over here, just you see this expression A inverse A, that is actually the identity matrix. Let's copy and paste this expression. So this is the feature that has to be adjusted in anyway. So over here, A square A is equal to A inverse A is equal to the identity matrix I. Again over here, A inverse into A square, that means A into A. This A square can be written as A into A. Now this A inverse into this A, that would become is equal to the identity matrix. Again over here, A into A square is actually A cube. So over here, this A inverse into A, this expression would also be the identity matrix. Okay. Now what we need to do, sorry, sorry, I made a mistake. That is a square. Is square. A square. Now this I into a square is equal to simply minus a square. This is 5a. Let's keep it as 6i, and then this is 5a inverse. We have this type of relation, and from this relation, this 5a inverse would be is equal to, just keep these terms on the right hand side, shift these terms on the right hand side. So what we have a square minus 5 into a plus 6 into this identity matrix, 6 into identity matrix. Therefore what is a inverse? This a inverse, is equal to 1/5 of each term, 1 by 5 of this first term. This would be simply a, and that would be 6 by 5 into this identity matrix. So in this fashion we will be able to compute a inverse. Now it is a matter of only computation of this part. So here we need to compute a square. You can check that this a square would be is equal to the determinant. Let me just copy and paste from here. I am leaving this computational detail for you. Okay, this would be is equal to minus 2. This would be 1, and this would be 4, and the next term would be 3, 1. This term would be is equal to 3. Then we have it would be minus 5. It is 5. And this is equal to 14. You can check that a square would be is equal to this kind of determinant. And once you get the expression of a square, then you have already the expression of capital A. So therefore we can say, we can just put all these expressions and compute uh, the expression of A inverse. So 1 by 5 a square. Just let me copy this one and write it over here. 1 by 5 into this kind of determinant and this kind of matrix minus A. So what was A? This was the given matrix capital A. So minus this matrix capital A plus 6 by 5 into I. I means third order. Over here all these matrices are of third order. So we shall have to write 6 by 5 into this kind of matrix, the identity matrix, 3 by 3 identity matrix. Matrix, not determinant. Okay, matrix. So 1 0 0 0 1 0 0 0 1. So we actually have this type of expression, and let's see, just no, it is not working. So now in this fashion, if you compute this total technique, ultimately you will get that A inverse would be is equal to, you can check the computation process, that A inverse would be is equal to this kind of matrix. I am skipping some computational steps. It would be 4 comma 1 comma minus 1, then minus 12 comma 2 comma 3, and then the last term would be 5 into 0 5 0 0. 1 by 5, do not forget to write this 1 by 5. This would be the A inverse, or particularly speaking, this kind of expression, everything has to be divided by 5. So this would be the expression of A inverse, the matrix A inverse. So in this fashion, if we apply Cayley-Hamilton theorem, then we can compute the expression of A inverse. Let's start with this kind of example. Let us consider the system of linear equation. The system of linear equation like this kind of system set 2x1 minus x2 plus x3 that maybe is equal to something like that. Say, I don't know, arbitrarily I'm just putting 2 over here. Okay. Then the next one is equal to 3x1 plus 2x2 plus x3 is equal to, say, I'm putting how much? Let's put 6. Okay. And finally, x1 minus 4x2 plus 5x3 is equal to, suppose this is equal to 0. Okay. In exam at least mostly 3 by 3 system comes, but remember in this kind of systems over here it may so happen that sometimes one relation can be expressed as the summation or subtraction of remaining relations. It may so happen, and if it happens, in that case one relation, maybe the first relation or the second relation, whatever it is, one relation would be an extra relation, and in that case number of variables will be equal to 3, but effectively we actually have only 2 equations. In that case also we have a mechanism to solve this kind of systems. And if it is if all these relations are not extra, no extra relation is there, then we have 3 equations and 3 variables. Sometimes this kind of equations can be solved by the help of Cramer's rule, but over here it is given that we have to use the row reduced echelon form. That means we have to apply the sweep out row operations. Now you see this kind of linear system can be written in this way, that this can be written as, you see, if suppose capital A with a coefficient matrix, its coefficient matrix is capital A. Capital A is equal to, that would be 3 cross 3 matrix. These coefficients will construct this matrix. So that's 2 minus 1. Oh, I made a mistake. It would be 3. And the right hand side would be is equal to 4. 2 minus 1, 3, and then 3, 2, 1, and then 1 minus 4 and 5, like this. And along with this matrix, if you consider the right hand side expression and the right hand side as this vector, say let us call it B vector. B vector is equal to a column vector. these elements 4, 6, 0. Okay, 4, 6, 0. All right. Then you see what we can write this expression. You see, I'm making some rough calculation over here. You see this right hand side, or you can say this left hand side. You can start with this left hand side. This left hand side. These are three expressions, three relations. Now let me write column column vector. This is the first expression. Let's write this column vector over here. Then this is the second expression, and this is the third expression. Okay, and what are their values as per the given question? This right hand side 4, 6, 0, is value is equal to this vector b. This is actually the b vector. And what is this left hand side? This left hand side, you see, this left hand side can be written as the matrix capital A into a determinant, into a column matrix like x1, x2, and x3. So if we suppose that this expression is equal to maybe this vector capital X, therefore you see this expression capital A into X, this expression can be written in this way: capital A into X is equal to the right hand side B. So that is the expression Ax is equal to B. Therefore a system of linear equation can be written in terms of matrix form like this: Ax is equal to B. Okay, and in order to solve this kind of system, what we consider, we consider the augmented matrix. What is augmented matrix? We make an augmentation, or we add something into this coefficient matrix. What is this? It becomes is equal to, we generally write this augmented matrix by this kind of notation: A, B. Or you can simply write it by capital B, augmented matrix. What we do, we actually over here consider this coefficient matrix, and we add a column on the right hand side. So let's insert a column on the right hand side. And what are the elements of this column? This right hand side expressions 4, 6, 0. This would be the elements of this kind of matrix, the augmented matrix. In many books you will find this expression A suffix B is also written as augmented matrix, or sometimes it is simply written as A B. Whatever notation you consider, let's for simplification consider this notation B. Now on this augmented matrix we apply the sweep out row operations. So over here we can check using sweep out operation, sweep out row operation. We get what we get. You see, let's subtract. Let's subtract this third row from the first and second row. Did I make a mistake? I think I made a mistake over here. No, it's okay. Rather, first I'm trying to make this one 0. Okay. How to do this one? You see, let's see. I'm trying to make this third last row, this one, these three elements 0. Let's check whether it is possible or not. And sometimes it may also be, it may also happen that you get certain absurd results, and in that case this kind of linear system does not have any solution at all. Let's check whether it is possible over here or not. So in for super operation, what we write, we use this kind of tilde notation, and let's try to subtract this third row. Let's try to subtract this third row from first and second row. What we do, if we multiply this third row by 2, multiply by 2 and then subtract from the first row, then what we have, if we multiply this row by 2, then 2 minus 8, then 10 would be there, and then subtract. What we will get? 0, then this subtracted from minus 8, then we will have plus 7, and this subtracted from 3, we will get minus 7, and 0 subtracted from 4, it would be simply 4. So that is the result we have over here. So this first row will be 0, 7, minus 7, and 4. And next we multiply this row by 3 and then subtract it from this second row. So what we shall have? 3, then minus 12, and it will be 15, and then subtract it from this second row, so that we shall have 0, subtraction, so minus plus 14 would be there, and again 1 minus 15, that is equal to minus 14, and 6 minus 0, that is actually 6. So in this way, again we have the manipulation. So this would be the result. Got it? Now you see 7 minus 7 4, and 14 minus 14 6. Over here we got a non-zero relation, a non-zero number. So now what we are doing, we are making the manipulation that this row is to be subtracted. Actually, this row is to be multiplied by 2, and then it is to be subtracted from this second row. Okay, let's copy and paste this over here. Now I am multiplying this first row by 2, so that we will have 14 and minus 14 over here, and it would be 8, and then subtract from the second row. So after subtraction, this expression would be equal to 0. This is again 0, and after subtraction we will have minus 2, and that is a problem over here, because I did not consider the right hand side properly. What is the problem? Let's check the problem. And the first row was this. So I need to modify this right hand side a bit, so that the problem becomes consistent. And by this kind of manipulation, you see this expression, this first row and second row and third row, these 3 rows can be written in this fashion, like this, or as a simple case. This first row would be 0 into x1 plus 7 into x2 minus 7 into x3 is equal to 4. So 0 into x1 plus 7 into x2 minus 7 into x3. Then the second equation would be 0 into x1, then 0 into x2, then 0 into x3 is equal to minus 2, and that is actually an absurd result, because it should not be true that 0 into 0 into 0, all this should be 0, and that should match over here with this right hand side. So this right hand side should be 0. However, in exam this kind of question may come. It is not a wrong question, actually it has a different kind of answer. Anyway, let's first complete this third row. So 1 into x1 minus 4 into x2 plus 5 into x3 is equal to 0. Okay, fine. Now over here, what happens if you get this kind of relation where the left hand side is equal to 0 and the right hand side is not equal to 0, then what you need to conclude? You need to conclude that the second relation says that the given system does not have any, or firstly you can say that the given system is inconsistent, and so it does not have any solution. This would be your final conclusion. But over here, as I got that yes, the question was wrong, so I am trying to write the in place of this 6. In place of this 6, I am trying to write something so that we get a consistent result. That means the right hand side becomes is equal to 0. Let's check what we can do. You see, we got minus 2 by subtracting 2 into 4 from this 6. So we got minus 2. So if I write 8 over here, in that case I think this would be 0. So the second element, let's modify the right hand side. Suppose this is 8. In that case, this vector would be is equal to 4, 8. And I think now it is consistent. Okay, 0, 0, 0. This is actually 0. 0 is equal to 0. Even you, in that case, you don't need to write this second equation at all, and now it is a consistent relation. So the conclusion would be a bit different. You can now compute the solution. What happens? You see, 7x, now let's make it simple. 7x2 minus this is useless, so let's delete this one, and so we have this kind of relation. And now from this kind of relation we have two equations and 3 unknown quantities. And over here you can further make one more manipulation if you want. You can make either this term or this term is equal to 0, or you can keep it in this fashion, whatever you want. Here, now from this relation, what we have from this relation, from the first relation, we have from first relation, we have what we have, x2. You see, x2 can be written as x3 plus 4 by 7. And in that case, what would be x1 from this second relation? Then second relation gives x1 is equal to how much? 4x2 minus 5x3. So we already got the expression of x2, so we just put this expression of x2 over here. So that is equal to 4 into this kind of expression minus 5x3, and let's make it simple. That is equal to 16 by 7 minus x3. So over here you see x2 and x1, both of these two quantities have been written in terms of x3. So if we assume that x3 is equal to some arbitrary quantity like c, where c is any arbitrary constant, C is an arbitrary constant. Then what we have, x2, or let's first write x1. Then x1 is equal to, that would be 16 by 7 minus c, and x2, sorry, x2 is equal to this kind of value. In place of x3 I am putting c. So x2 is equal to this kind of value. Therefore the given solution, therefore the required solution, therefore the required solution of the given system is, you can write it in this way, x1 is equal to this kind of expression, then x2 is equal to this kind of expression, and what is x3? x3 is equal to this c, where c is an arbitrary constant. Okay, so in this way you can apply this sweep out row operations, and applying this kind of sweep out row operation, you can find the solution of this system of linear equations. So this is the technique I wanted to discuss. And if the number of if over here you see this second relation becomes an extra unnecessary relation, and if you get all this are 0, then only you get this kind of extra unnecessary relations. So in that case you don't need to bother about these extra unnecessary relations. Just you consider on the non-zero contributions, and from this non-zero contribution you will ultimately get the final reduced or simplified expression involving x1, x2, x3. And that from that expression you can directly compute the expression of these variables, or you can directly compute the values of these variables. So in this way you can compute the final solution of the system of linear equations. So that's all for this lecture. Thank you for being with us.